Hello everyone, I'm a third-year PhD student from the University of Manchester, and today I'm going to talk about my PhD project on Amphiphilic drugs, beta blockers, and their interaction with model biomembranes. We aim to study a series of beta blockers to explore the structural functional relationship. So first I'll talk about the background and the aim of the project and also the reason why we want to study this. First, some amphiphilic drugs behave like surfactants and they can self-assemble in solution to form some micelle-like structures. And these kind of structures can play a significant role in moderating the drug's solubility, permeability, and therapeutic activities. Currently, many studies mainly focus on the drug-protein interactions, ignoring the possible existence that drugs might interact with cell membrane directly. So our study is to look at the self-assembly of amphiphilic drug in solution and also the interaction between the drug and model cell membrane. The model cell membrane is to take one or more lipids to approximate lipid composition of a cell membrane. And the drug we studied here is beta blockers, which can block the activity of beta adrenaline receptors. As the structure shown here, most beta blockers have hydrophobic tails and hydrophilic heads, and some of them are reported can self-assembly in solutions. So we start our study from the most famous beta blocker, propranolol hydrochloride. The structure is shown here. It is reported to have a critical micelle concentration of around 100 millimolar with, using the light scattering method. Here we use the warming plate method to measure the surface tension of the drug. And the warming plate method is to measure the force on the plate bent from the weight of the wetting liquid. And we measured a series of the concentration of the drug in both in water and in saline, which equals to 0.154 molar sodium chloride. The critical micelle concentration is 92 millimolar in water and 57 millimolar in saline, which suggests that the surface activity of the drug is stronger in when there's salt present. Um, the minimum around CMC in the surface tension curve can be referred to the surface active impurities, probably one never saw in this case. We have already purified the drug before we measured it, but it seems that we need further purification. Um, to study the self-assembly of the drug in solution, we use a technique called small angle neutron scattering. Neutrons are good to study the bulk properties of a material because they can deep penetrate into an atom without being affected by electrons due to the strong nuclear force when interact with nuclei. Um, the two figures here shows the nuclei by X-rays and neutrons respectively, which is related to the refractive index of different atoms called scattering lengths. The scattering lengths of hydrogen and deuterium are very different by neutrons, which provide a way of using isotopic contrast to study the composition of a material. So in our study, we use proteated drug and ring deuterated propranolol hydrochloride. This plot shows the variation in neutron scattering intensity of propranolol hydrochloride at 3 different concentrations. Actually, we measured the concentrations from 200 millimolar down to 10 millimolar, but here only shows 3 concentration points above the CMC values, and there are 4 contrasts for each concentration, which is H drug in D12, D drug in H2O, H drug in H2O, and D drug in D2O. What is very impressive is that we can even get scattering for H drug in H2O, which is normally too low to be detected. And this helped us to save quite a lot of money. Now back to the data. We linked all four contrasts for each concentration and model them in a shape or in a shape of prolate ellipsoid, and assuming there is a core that mainly composed of hydrophobic rings. And the details of the shape we'll talk later. But here, I want to talk about the shape of the curves that indicates there are some interparticle interactions between the particles. So the particles are charged. So we use the Hater and Penfold model to calculate the structure factor of charged particles. The aggregation number is obtained by dividing the core volume of the aggregates by the volume of the ring structures in a single molecule. And the aggregation number we obtained for 170 millimolar is about 18, while for 150 and 130 millimolar they're both 9, which indicates that the aggregates are likely to grow larger in higher concentration. Besides, because smaller aggregates might be blended by larger aggregates coexistent in the system, therefore the aggregation size we obtained from the neutron experiment is roughly the maximum size of the that's averaged over time of the drug. So we also applied molecular dynamic simulations to better understand the self-assembly of the drug, and the plot in the left shows the size distribution of the aggregates from 200 millimolar simulation results. It seems that the maximum size are much higher than the mean and medium size, which suggests that the size of the aggregates are very poorly dispersed. And we also plotted the average aggregation number of each concentration, which also confirms the experimental results that the aggregates are likely to be larger in higher concentrations. Then about the shape of the aggregates, we picked one cluster from the 200 millimolar simulation results, and it seems that the aggregate is roughly in prolate ellipsoid with a core that mainly composed of ring structures. So we modeled the data at same concentration using this shape, and the aggregation number we obtained for 200 millimolar is 20, which is roughly in accordance with the aggregation number we obtained from the computational results of 18. And it also confirms that our experimental results can in accordance with the MD simulation results. Then the second part of my project, the interaction between the drug and the model cell membrane system. The model cell membrane we used here is a lipid monolayer on air-water interface that composed of POPC with and without cholesterol. The variation in surface pressure and ellipsometric phase shift were recorded at the same time using the combined Langmuir trough and ellipsometry. The trough is filled with subphase where lipids are spread on top and compress the two barriers to make the surface pressure in the monolayer close to the surface pressure in cell membrane. And then we inject the drug into the subphase to interact with monolayer. The right figure shows the optical path length of laser in ellipsometry. The polarized laser reached the surface of monolayer and reflected back up and refracted through the film. The phase upon reflection is called delta, while the extra path length caused by refraction is called d delta, which is related to the thickness of the film. And because the laser beam is very small, the inhomogeneities in the film can cause fluctuations in signal. Here it shows the surface the variation in surface pressure and ellipsometric phase shift of a POPC cholesterol monolayer interact with 20 millimolar drug, which is much lower than the CMC value. The surface pressure data is very interesting because it can give information like drug absorption and lipid loss. The drug absorption can be seen from the increase in surface pressure after the drugs were injected. And with the increase in salt concentration in subface, the interaction seems to be stronger and faster, which indicates that the existence of salt can promote the interaction between drug and monolayer. Besides, the ellipsometric phase shift reflects the inhomogeneities in the film, which is related to the formation of lipid domains. And because the fluctuations are much stronger in lower surface pressure, it might suggest that the drug have preference to lipids when interact with the lipid monolayer. And to better understand the interaction and where the location of the drug in the monolayer, we applied neutral reflectivity experiments. Neutral reflectometry is a technique that used to study the composition of multiple layer systems. It can provide information of the thickness, the roughness, and the hydration in each layers of the system using the reflectivity and the scattering length density profile. The data here is the POPC membrane interact with 20 millimolar drug. It is the same data but with different models. In the left, it shows the model of no drug, and in the right, it is the best model that fitted with the experimental data. And because the scattering length density of the lipid heads and tails are very different, so we regard them as different layers and add drugs into either tails or heads or both tails and heads to see which one fits the data best. And the result shows that there were 70% of drug penetrated into the head group region of POPC monolayer. And here it is the data of POPC cholesterol monolayer interact with 20 millimolar drug. When we model this system, we assume that cholesterol only has a hydroxyl group in the head group region of lipids, and the result here shows that there was 35% of drug in the head group region of POPC cholesterol monolayer. Therefore, it is obvious that the existence of cholesterol affects the interaction between drug and POPC significantly. And because these data were obtained after the interaction, so we also applied kinetic neutral reflectometry to resolve what is happening during the interaction. And we also plan to do some bruised angle microscopy, which is an imaging technique to obtain the lateral morphology in micrometer scale. And now we come to the conclusion. In aqueous solution, the propranolol hydrochloride can grow larger with concentration, and the size of the aggregates are very polar dispersed. Besides, the shape of aggregates is roughly in prolyl ellipsoid with a core that's mainly composed of ring structures. From the interaction study, propranolol hydrochloride interact with model biomembranes by binding to the head group region of lipids and probably have preference when interact with lipids and also altering the orientation of lipids to form lipid domains. And under physiological conditions, which means in saline, the existence of salt can promote the self-assembly and the interaction with model biomembranes of the drug. Now, some future works to talk about. As I said before, we are going to use booster angle microscope to obtain some lateral information of the drug membrane interaction. And also we plan to do some molecular dynamic simulations of the drug membrane interaction as a complementary of the experimental data. And we also want to extend our study to another beta blocker, atenolol hydrochloride, to explore the structural functional relationship of a series of beta blockers. Now I want to thank my Professor Jane Lawrence and Dr. Richard Campbell and all other people that helped me with my project. Thank you for listening. Any questions?